Well, in section 5 we'll talk about the orthogonality of the four subspaces. I've already introduced this so that you could check your results when you do computations of the four subspaces. We'll talk about projections. We'll talk about least squares approximation, and then finally we'll introduce the Gram-Schmidt procedure to find the QR decomposition of a matrix, and we'll see that this QR decomposition can be used, for instance, to implement the least squares efficiently in some cases. Well, we can talk about orthogonal subspaces when the two subspaces are such that every vector that is in the first subspace is orthogonal or perpendicular to every vector in the other subspace. Okay, so here we have two subspaces V and W that are orthogonal, and this means that for every V and W the scalar product VW is equal to 0. So you can also write it in a matrix kind of notation, or you could even write it like this, right, is equal to 0. Well, first we show that the null space of A and the row space of A are orthogonal. Remember that these two spaces are subspaces of Rn. Okay, we will show this in two different ways. So X is in the null space, so this means that Ax is equal to 0. Okay, so we'll use here the row interpretation of the product Ax, and this produces a vector in which each element is the scalar product of X with the corresponding row of A, and we know that this vector is 0. So this means that X is perpendicular to every row of A. So it is also perpendicular to every combination of the rows. So X, which is in the null space, must also perpendicular to every element in the row space. So we can say that the null space and the row space are orthogonal. Okay, let's do this a little bit differently, and we know that the row space is obtained by taking linear combinations of the rows of A, or equivalently linear combinations of the columns of A transpose. Okay, so if you take vectors A transpose Y, they are in the row space. We'll now take the dot product or the scalar product with an X in the null space. Okay, so this is what you see over here. I'm using this other notation. Remember that X scalar product with Y, you can rewrite it as X transpose Y. This is what we are doing over here. Here we remember that A, B transpose is B transpose A transpose. So we rewrite this X transpose A transpose, and we use associativity to rewrite things like this. And we know that X is in the null space, so Ax is equal to 0. Okay, so we have just proven that every vector Y that is in row space is perpendicular to any vector X in the null space. Well, we'll do something very similar and prove that the left null space of A is perpendicular or orthogonal to the column space of A, and both subspaces are subspaces of Rm. So we'll use two ways to prove that. We'll take Y that is in the null space of A transpose, the left null space. So we have that A transpose Y is equal to 0. We can again use this row interpretation of this product over here, and we see that the result is a vector where each element is computed from the scalar product of a row with y, and we know that this is equal to 0. So y is perpendicular to every row of A transpose, so y is perpendicular to every column of A. Okay, so we have just shown that y, any y in the left null space is perpendicular to any linear combination of the columns of A. So the left null space and the column space are orthogonal. Okay, so we know that the column space is generated by taking linear combinations of the columns here for any vector x. Ax is taking linear combinations of the columns, and now we make the dot product or the scalar product with a y that is in the left null space. Okay, so this is what we are writing here. We can write it again differently. V scalar product with y is V transpose y, so we write it like that. We know that A B transpose is B transpose A transpose. By now you should know all these things, so you obtain this expression here, and y is in the left null space, so this is here 0. Okay, so we have just proven that any vector that is in the column space, okay, is perpendicular to any vector that is in the left null space, or that the left null space and the column space are perpendicular. So let us take a subspace W of a vector space V. Well, the orthogonal complement of W in V, and it will be denoted like this, is the set of all vectors in the vector space V that are perpendicular to the vectors in W. And this leads to the second part of the fundamental theorem of linear algebra. Well, the null space of a matrix is the orthogonal complement of the row space of that matrix in Rn, and there are both subspaces of Rn. The left null space is the orthogonal complement of the column space of that matrix in Rm, since they are both subspaces of Rm. Well, remember, if you can find n independent vectors that are in Rn, they must span Rn, so they form a basis of Rn. So one way to construct a basis is to take R vectors coming from the row space and n minus R vectors coming from the null space. Okay, they will be independent, so they form a basis of Rn. Okay, so if they form a basis of Rn, this means that any vector x can be written as a linear combination of these basis vectors. Okay, so this means that this vector in Rn, and this is true for any vector of Rn, can be written as a linear combination of the R vectors coming from the row space, so this must be a vector in the row space, plus linear combinations of the vectors in the null space, so this must be a vector in the null space. Okay, so any vector in Rn can be written as xr in the row space and xn in the null space, and these two vectors, since they belong to the row space and the null space and these are orthogonal, well, these two vectors are also orthogonal, perpendicular. Well, remember this picture where we had Rn over here and Rm, and the idea was that if you take a x where x is in Rn, well, ax will be in in Rm. Okay, so A was taking a vector from Rn and bringing it to Rm, and you could do the inverse also with the matrix A transpose Y, okay, with Y in Rm. Well, this leads to vectors that are in Rn. Okay, so by now we have added this thing here. This was announced previously, and we've seen that the row space is the orthogonal complement of the null space in an Rn, and the column space is the orthogonal complement of the left null space in Rm. And we have seen that any vector in X can be decomposed in a vector in the row space, okay, and a vector in the null space. You remember that, well, A times a vector in the null space will produce 0. So AXN will be sent to the origin over here. Okay, and this vector in the row space will be sent to some vector here in the column space. So we'll have AX in the row space is equal to some vector B in the column space. And we had seen here that XR and XN are perpendicular, they are orthogonal. So this is how you see things here. So we had seen that the null space component Xn was sent to the origin of Rm using this matrix A. The row space component, which is XR here, is sent to some vector B that is in the column space. And what we want to show here is that this vector B comes from one and only one vector in the row space. Okay, so assume there are two vectors in the row space that are sent to the same vector in the column space. So this means that this equation must hold. Well, this means also that the difference between the two vectors XR and XR prime, okay, which are vectors in the row space, must also be in the row space, because a linear combination of two vectors in the row space must also be in the row space. So the difference here is in the row space, but writing this equation is equivalent to writing this equation, okay, and this means that the difference XR minus XR prime is in the null space. And the only way that you can be in the null space and in the row space is if this vector XR minus XR prime is the 0 vector. That's the only vector that is in the row space and the null space. So this means that XR and XR prime here are identical. So we have shown that every vector in the column space comes from one and only one vector in the row space. So we want to talk now about projection, and first we'll talk about projection on a line in Rm, and this is something that we had done previously and we found of course the same result, but now we'll find it in some other way. Okay, so here is the line in Rm represented by the vector, and we are looking for the projection of B on the vector A, and that's P. And the key here is orthogonality, and we see that the vector E here, which is the difference between B and P, is orthogonal to A and orthogonal of course to the projection. So we'll write the projection P here as some multiple of the vector A, and this multiple is x hat here, and this is the, well, in this case, scalar that we are looking for. So the error is b minus p. We can write p as a multiple of a, so e is written like that, and it is perpendicular to a, so you can write this equation over here. Using distributivity, you obtain this equation over here, and now we have to isolate x hat, and this leads to this equation over here. Okay, so this is using the scalar product, and this is using, well, the matrix or vector notations. Without a surprise, it's the same result that we had obtained at the beginning of the course. So in the previous slide we were looking for the projection of b onto a vector A, and now we are kind of interested in the matrix that will map b into p. So remember that the projection could be written as a multiple, okay, of the vector A, so A times a scalar. You can of course rewrite it like this, okay, by multiplication by a scalar is commutative, and remember that x hat, this multiplier, is given by this thing over here. So now we would like to write the matrix that P, the projection matrix that will map B onto its projection, okay, and this is this matrix over here. Okay, this is the projection matrix. So remember that A is a column vector in Rm. So here on the numerator you have a column vector times its transpose. So this will have m times 1. This is 1 times m. So this must be a matrix in R m times m. Okay, so this is A transpose. A transpose A is this thing over here. Okay, so this is 1 times m, and this is m times 1. So this is a scalar. Okay. So on the numerator you have an m by m matrix, and on the denominator a scalar. So we have found that the projection matrix is a m by m matrix, and it's a rank 1 matrix. We have seen that if you can write a matrix u v like u v transpose, then it is a rank 1 matrix. Okay, well, here this is obviously the case because we write the projection matrix as this divided by a scalar. So the projection matrix is a rank 1 matrix. Well, if we project B on A and we obtain P, okay, and we project P on A again, well, of course we obtain the same vector P. So this means that P square must be equal to P. So projection matrices have the following properties. Well, let us take a very simple example where we project in R2, on a line in R2, so that we can represent things. So B is projected on A. So remember that the multiplier, well, it's scalar product of A and B divided by the scalar product of A by itself. This can be written in this, well, vector notations. A transpose B, this will lead to 1, 3 plus 2 is, well, it's a 5 over here, and the scalar product of this one by itself will give you, well, 10. Okay, so indeed this gives you a half. So the projection is this multiplier times the vector itself, and this leads to this over here. Okay, we could also write the projection matrix, and the projection matrix is A transpose divided by A transpose A. We already know that this one is 10. Okay, so it's 1 over 10 times, well, the vector 3, 1 times its transpose. So you will have 0.9 over here, 0.3, 0.3, and here 0.1. Okay, so this is the projection matrix. And if we use the matrix P and we apply it on B, well, we should have the same result as below. So let's try that. 0.3, 0.3, 0.1, and we take the vector B, it's 1, 2 over here, and this will lead to, well, 1.5, and here 0.5. Okay, and so this is indeed equal to what you have here below. So you see that working with scalar products is easy. In the next slide that I will skip, you can see that if you start working with cosines and things like that, things become a lot more complicated. Okay, we'll do something slightly more complicated right now. We'll project B onto the column space of the matrix A. So why do we need this? We'll remember that we are interested in the system of equation AX is equal to B, and we know that there is a solution if B is in the column space. If B is in the column space, we know that it can be represented by a linear combination of the columns of A. So the solution will be this particular linear combination. So what happens if B is not in the column space? Well, obviously there is no solution to the system AX is equal to B, but we are kind of interested in the best approximate solution, and this will involve projecting B onto the column space, and this is precisely what we are doing over here. So assume that A is in Rm times n, so m rows, n columns, okay, and we assume that the n columns are linearly independent. So in our case, we'll represent things when m is equal to 3 and n is equal to 2. Okay, so then if we have two columns of 3 elements, we can kind of represent the column space. It will be represented by this plane over here. If m is larger, well, then it's kind of difficult to represent things, right? And then we have a vector B, and since we are talking about projection, of course B will not be in the column space. Okay, so it's also a vector of Rm, so it's in this case, in the representation, a vector of R3, and we are interested in the projection of B onto the column space of A, and this will be the vector P. Obviously P, since it's a vector of the column space, can be written as a linear combination of the vectors which are the columns of A, and it can be written like this, right? It's x1 hat times the first column plus x2 hat times the second column, and so on. Well, writing P as a linear combination of the columns of A, well, you can also write it like this. Remember this column interpretation of the product of a matrix and a vector, this is simply saying that the resulting vector is a linear combination of the columns of A using the coefficients in X hat. Okay, and again we'll use orthogonality. We'll say that the error B minus P is orthogonal to the projection P. P is in the column space and P times E is equal to 0. So the error vector must be in the left null space. So E is B minus P. P, we've just written it as a linear combination of the columns of the matrix A, so we can write E like this. It's orthogonal to P, so writing P scalar product with E is equal to 0 is the same thing as this thing over here is equal to 0. So this is P transpose, you know the property of the transpose by now, and this is E. So if we distribute things and we put this one up front, we have X hat transpose times A transpose B minus A transpose A, X hat is equal to 0. Okay, so this means that this must be 0, and this leads to this equation over here. This is a matrix that is square. We have seen this previously, and since the columns are linearly independent, okay, this matrix has an inverse. So we can compute X hat using this equation over here. The projection is A times X hat, so we inject X hat over here and we obtain this expression. And if we are interested in the projection matrix, well, it's this matrix over here. Remember that the projection matrix is the matrix that transforms B into its projection, in this case here in the column space. Okay, let's summarize things. We are projecting B onto the column space of A, and this will produce P, okay, which is in the column space, so we can write it as a linear combination of the columns of A, and this can be written like this. So it's in the column space of A. The error, which is the difference between the original vector that we are projecting and its projection, P, we'll write it as AX hat. Well, it is perpendicular to P, right? So, since P is in the column space, E must be a vector of the left null space. Okay, so remember that the column space is a subspace of Rm, that is the orthogonal complement of the left null space. So E must be in the left null space, and the left null space, well, it's all vector y such that A transpose y is equal to 0. Okay, so this means here that A transpose E must be equal to 0. So here you have E, and here we obtain this equation that we have obtained in the previous slide, but a little bit differently. So this leads to X hat is equal to A transpose A inverse times A transpose B. This is what we had obtained in the previous slide. So what have we done? Well, we have decomposed the vector B into two orthogonal vectors one that is in the column space, that's the projection we are looking at, and another one that is in the left null space, and that's of course the error, and we are thereby producing kind of a right triangle. The distance of B to the subspace column space of A is, well, the length or the norm of the vector E. So remember that A in general is a rectangular matrix. It has m rows and n columns. So this product over here, A transpose A, is such that, well, you have an n by m matrix times an m times n matrix. So it must be a square n by n matrix. And we know it's invertible because we have said that we have required that the columns of A are independent. So another way of saying this is that A has full column rank. So this matrix is invertible, and we can write this estimate x hat. So here's the summary. We're taking B in Rm and we are projecting it on the subspace, which is the column space of A. A is a rectangular matrix of dimensions m times n, and the projection is given by this thing here, where x hat is obtained over here. If we are interested into the projection matrix, which is the matrix P that will take B to its projection, well, you're seeing it over here, and it leads to this matrix over here. It's an m times m matrix. You could take all dimensions of A transpose and so on and find that it is indeed an m by m matrix. But it's maybe easier to see that this is in Rm, and the projection is also in Rm. Okay, so it means that P must be a square matrix that is m by m. If you project B onto the column space, you obtain P, and if you reproject it again, you obtain again P. So we have also this property that P square is equal to P. So we are using this now to find what is called a least squares approximation. Okay, very often you end up with systems of equation Ax is equal to B where there is no solution. There are many equations, actually too many equations for the number of variables that you have, and A is a tall matrix. Okay, so m, the number of rows, and n, the number of columns, is such that m is much larger than n. Okay, there are more equations than unknowns, and the column space, okay, which is the combination of all the columns of this matrix A, will spans only a part of Rm. And usually, since there are lots of equations, okay, and fewer variables, B will not be into the column space in this case. Okay, so this means that if you use elimination, you'll find that, well, it's impossible to find a solution. There is no solution, and elimination just stops. This means that this error vector Ax minus B will not go to 0. And as I've said before, well, there is no solution, but we would like to find kind of the best approximate solution. So we would like E here, the error Ax hat minus B, to be as small as possible, and this is where projection comes into play. And this x hat that we've introduced before, it's the least squares solution. Well, in the previous section on projections, we had put the focus on the projection itself, right? But in this subsection, we are interested in the solution, the least squares solution, x hat over here, and of course they are connected by this equation. So how can we arrive easily at x hat? Well, you can use this quick and dirty way to arrive at the solution. You write ax equals b, you pre-multiply both sides by a transpose, you obtain this equation, and this leads to the least squares solution. Well, it's kind of implicit, but this matrix over here must be invertible, and this is indeed the case if the columns of A are independent. Okay, another way of seeing this is that the error, the norm of the error here, is as small as possible, so it's minimum. So one way of computing x hat is to simply say, well, I'm going to take the partial derivative of e here with respect to x. This goes a little bit beyond the course because it involves taking derivatives with matrices and things like that, but if you look at the literature, you will see that this derivative here is given by this equation, and if you impose this partial derivative, or these partial derivatives, because there are more than one, and since x is a vector, well, if you impose this to be equal to 0, of course what you'll find is again this least squares estimate. You will see that a lot of problems can actually be written as least squares problems, and this explains why this method is so popular. Well, fitting a straight line through m points is an application of least squares approximation. So the straight line is this one over here, and these are the unknowns, right? And we would like this straight line to go through these 3 points over here. Okay, we already see that unless we are very lucky, it will be impossible because we only have 2 variables and we have 3 constraints. Okay, so when t is equal to 0, this leads to the following equation: c plus 0 times d is equal to 6. The following point leads to the constraint c plus 1 times d is equal to 0, and the next point, t is equal to 0, 2, leads to 2c plus 2d is equal to 0. This can be written in matrix form: ax is equal to 0 with a and b over here. Okay, it's very easy to see there is no solution because b is not in the column space of A. You can see very easily that you cannot write B as a linear combinations of the columns of A. If you want to produce a 6 over here, you need to take 6 times this first one, okay, and it's impossible then to have a 0 below because you have different elements over here. So in general, in this case here, there is no solution. You can compute the least square solution, which is this one. I will come back to this later on, and the projection, that is simply a times x hat, and we'll obtain x hat using 3 different interpretations: a geometrical interpretation, an algebraic interpretation, and a calculus interpretation. So in geometry, we'll really fit a straight line through these 3 points. In algebra, well, we'll split the vector b here in perpendicular components, one that is in the column space and one that is in the left null space. And with calculus, well, we'll set partial derivatives of this quantity e that we've talked about previously to 0. So let's look at the geometrical interpretation. So we have a point, in general, well, the original points are given in red. So you have here 0, 6, you have 1, 0, and 2, 0. And the projections are given in purple over here. Okay, so they are 0, 5, they are 1, 2, and it's 2 minus 1. Okay, so geometrically we want the best line to be such that the sum of the errors squared is as small as possible. So we want e1 squared plus e2 squared plus e3 squared to be minimal. Okay, and we were looking for a line C plus dt, and the coefficients C and D that will make this as small as possible are the solutions of the least squares problem. Okay, so B was 6, 0, 6, 0, 0. The projection here is 5, 2, minus 1. Okay, and you can see that the error vector is 1, minus 2, 1. And you can see indeed that E scalar product with P is equal to 0. Okay, but this in this geometrical interpretation we want to play with this line over here, which is influenced by the parameters C and D in such a way that the sum of the error squares is as small as possible. Well, the algebraic interpretation is as follows. We split B into parts, one that is in the column space and one that is in the null space. So we split B into P plus E. This one is here is in the column space, and this one will be in the left null space of the matrix A. And indeed these are the two vectors P and E, and you can see that P scalar product with E is indeed 0. So AX is equal to B cannot be solved, but the equation that you obtained by considering the same thing with P over here, it can be solved, and the solution leaves the smallest possible error E over here. So if we draw things and we say that this is the column space, we have here our vector B here. Okay, it's projected on the column space, so this leaves P and this leaves E over here. So let's take any vector in the column space. It can be written as a linear combination of the columns of X. Okay, so this vector over here is AX minus P, and this vector over here is AX minus B. Okay, so we have here a right triangle, so we can write that the length of AX minus B squared is equal to the length of AX minus B squared plus E squared. Okay, and the least squares solution will make this term 0 over here. Okay, so this will be made 0 by X hat. And the vector E is of course perpendicular to the projection, but it's also perpendicular to any vector in the column space, so of course to the two columns here of A. And a third interpretation can be obtained using calculus. Remember that the error function that we want to minimize is the sum of squares. The 3 points were 0, 6, 1, 0, and 2, 0. And the straight line that we wanted to fit was this, of course. Okay, so if we want to minimize the sum of squares, we'll take this one here with t is equal to 0 minus 6, so it's z plus 0 times d minus 6 squared. This is e1 squared plus t is equal to 1 here, sorry, c plus d minus 0, c plus d minus 0 squared, that's e2 squared, and here t is equal to 2, so c plus 2d minus 0 is equal to squared, sorry. And so we have here our cost function that depends on c and d, so we can take partial derivatives with respect to c and d and impose that these partial derivatives are equal to 0. And if you go through the calculations, you'll end up with a system of equations, 2 equations and 2 unknowns, and it happens to be this system of equation that is the one that is underlying least squares. You can check that. Okay, so we can generalize this. Suppose we want to fit a straight line here, c plus dt, through m points, and suppose that these m points are ti, bi, or m points, so I is going from 1 to m over here. So we can write the equation. So you have c plus t1d is equal to b1. You have c plus t2d is equal to b2 up to c plus tm is equal to bm. So we can write this as a x is equal to b, where x is simply a vector containing c and d, and you have the matrix over here, a, and here you have the b vector, right? So now we can write this system of equations and find the least squares estimate and find c hat and d hat. So this is A transpose. A transpose A is very easy to compute. Once, a vector with once, times a scalar product with another vector. This will give me m. This one, this line, first line, times the second column of A will give me the sum of the ti's. Same thing for this element 2, 1 over here. And second line times second column will give me the sum of the squares of ti. You can compute A transpose B. You'll end up with something like that, and you find a very simple 2x2 system of equations that you can obtain very easily. So next time that you have to fit a straight line through m points and that you don't have MATLAB or Excel, this can be done rather easily, even by hand. Well, let's look at this perhaps more abstract view of least squares. We had the problem ax is equal to b, and b, as you can see, is not in the column space. So ax is equal to b has no solution. So what we are doing is decompose b into a vector P, which is in the column space, and a vector E that is in the left null space. As you can see, P and E are perpendicular. There was no solution for AX is equal to B, but there is a solution to the problem AX is equal to P. Okay, so there is a vector x hat here that is such that AX hat is equal to P, and this x hat is indeed the least square solution of this problem AX is equal to B.